we start. Still some more have to come. Okay, we can start. Okay, so last class we stopped at Hilbert-Nullstellensart's theorem statement. Once again, this class we will prove this. So the statement is, we have a polynomial ring in n variable over complex numbers. Any maximal ideal, a set of all maximal ideals in this ring are in bijective correspondence with points, n coordinate points, complex points in C power n. Okay, n variable and points in C power n. So given a point, we construct a maximal ideal, and from the given a maximal ideal in the polynomial ring, we construct a point. Okay, this is the way bijective correspondence. So it's very natural. Given a point means we have one very nice homorism, which is a substitution map from the polynomial ring to the complex numbers, which takes any polynomial to the value of the polynomial at that point. Okay, so we know that this is a ring homorism, surjective, etc. Therefore, the kernel is an ideal, we know. Okay, now we have to prove it is a maximal ideal, etc. And then the converse also we have to prove. Okay, this is the statement. So every maximal ideal is corresponding to a point in the point in C power n, and any point is corresponding to a maximal ideal in the complex polynomial ring. So we have seen already some preliminaries. Now we are going to see the proof. Okay. First, we start with a point. Given a point, a1, a2, an, n coordinates in each one is complex number. Given a point in Cn, we construct. We consider the substitution map from the polynomial ring in n variable to complex number C. Takes is a substitution map, and the substitution map is a surjective ring homorism, and the kernel is the ideal. We call it MA. Okay, corresponding to that point A. Okay, then the first isomerism theorem. So we know that since it is a surjective map, this quotient ring is isomorphic to the complex field C. So therefore, the ideal is maximal ideal. Okay, so the kernel of this substitution map is a maximal ideal in this case. What we need to prove is this maximal ideal is generated by x1 minus a1, etc., xn minus an. We need to prove this. Okay. Okay. So for that, first we take any polynomial, any element in the maximal ideal. We call it f of x1, x2, xn, which is nothing but the kernel of the substitution homorism. Already yesterday we have seen any polynomial in n variable we can write in terms of this way. I mean, instead of xi, you send it to xi minus ai. I mean, around ai, a1, a2, an, around the neighborhood, kind of you are rewriting this given polynomial. This way, we can able to write f of x1, x2, xn, the given polynomial. We can write it as f of a1, a2, an plus the linear combination of xi minus ai products also, 1 at a time, 2 at a time, 3 at a time, and many at a time. I comma j need not be distinct here. In fact, xi minus ai whole square also can come. Okay, some powers also can come, but linear combination of this. Since f is this f of x, the particular polynomial in the kernel of the substitution homorism, that means f of a1, a2, an is a 0. Okay, so therefore this polynomial f of x1, x2, xn we can rewrite in terms of just a linear combination of xi minus ai's. Okay, maybe the product, some product also. That is clear. That means f of x1, x2, xn is contained in the ideal generated by x1 minus a1, x2 minus a2, etc., xn minus an. Okay. So this is what this statement really says. That means f is a random element of the maximum, the ideal MA. So therefore, this MA is contained in this ideal generated by x1 minus a1, x2 minus a2, etc. Since MA is already maximal ideal, so this is either this is equal to this, or the ideal generated by x1 xi minus a should be the complex. I mean, should be the whole ring. If it is the whole ring, then it should have the unit element, which is not possible here. Unit element cannot be lie here. Okay, the same argument we have used before also. Therefore, this MA has to be equal to this ideal generated by xi minus ais. So what we have seen, given a point ai in Cn, okay, we have constructed a maximal ideal MA, which is the kernel of the substitution homomorphism, which is generated by xi minus ais, the linear polynomials, in linear monomials. Now, to finish the proof, we start with the arbitrary maximal ideal M, okay, in the polynomial ring. We need to prove that there exists a point in Cn such that this M looks like MA, nothing but the kernel of some substitution map. Okay, that's what we want to prove. So what we have is in hand just a maximal ideal in the polynomial ring in n variable. Okay, so by definition of the maximal ideal M, the quotient ring is a field. We call it K. Okay, then we look at the quotient map or canonical map pi from the polynomial ring to the quotient ring, which is a field K. Okay, so this is the canonical map we have. Because of maximal ideal, this map is going into the field K. For any R in between 1 and n, okay, so we are going to choose, I mean, there are x1, x2, xn are there. I'm going to choose that index 1 to n. I'm choosing arbitrary R, one element, one integer, index one integer, and I'm fixing that R. Okay, then I'm going to look at that xr, okay, the variable xr, and the polynomial ring in one variable with the variable xr. And since pi is this one variable polynomial is also a subring of n variable polynomial ring, we can restrict this map, this canonical map, to that particular subring. Okay, just a restriction map. Okay, so this I am calling it pi r. Pi r is nothing but the restriction map of pi to the one variable polynomial ring xr with the variable xr. This map is going from this one variable polynomial ring to the field K. This is a restriction of a homomorphism to the subring. Restriction of the homomorphism to the subring is a again ring homomorphism. Okay, just we are using that. What we are claiming, this kernel cannot be 0. Okay, this kernel of pi r cannot be 0, and kernel of pi r is a maximal ideal. So once it cannot be 0, and the second claim is that it is a maximal ideal generated by xr minus br for some complex number br. This second condition, once it is the kernel is non-zero, kernel pi r must be a ideal. Okay, if it is maximal, then we know that from the one variable case, once it is a maximal ideal, then it is generated by linear monomial only. Okay, that we know already. So we are claiming two claims. One is the kernel is non-zero. Okay, some non-trivial element is there, and the kernel phi r is a maximal ideal. These two claims we are making. Okay, suppose not. The first we are trying to prove. Suppose not. If the kernel pi r is just 0, it means it's an injection. Pi r is an injective map. Okay, the kernel is trivial, means pi r is an injective map. It means the polynomial ring C of XR is isomorphic to its image in K, inside the field K. Okay, so it means already, so the polynomial ring C of XR to K under pi r, this you get a image which is sitting inside polynomial ring. In some sense, this is this polynomial ring is sitting inside K, that we have. Already we know this, the field of fraction of this polynomial ring is the rational functions of in the variable XR. We know this is sitting inside the rational function field. Okay, that is, we call it phi. This is also injective map. The pi r is injective, phi is injective. Therefore, there is a unique homomorphism. You see, when we proved the universal property, in other words, C of R is the C of XR is the, I mean, the field of fraction is the smallest field containing the ring R integral domain. Okay, so by this there is a unique map, ring homomorphism from the rational function of XR to K. We get a map, okay, by the universal property. But that map is injective. Just because pi r is injective, phi is injective. That is the reason. Okay, so this means since C of XR is sitting inside the fractional field also, by the universal property, K contains a subfield isomorphic to the rational function in the variable XR. Okay, so we have to get a contradiction. Okay, so since just because we have assumed that the kernel pi of r is just trivial. Okay, since K is isomorphic to the quotient ring of the polynomial ring in n variable, and we know this polynomial ring in n variable has a countable basis. Just all the monomials powers, positive powers and non-negative powers. Okay, that is countable. So this is this particular ring has a countable basis. We conclude that K as a vector space over K as a vector space, this also has a countable basis, namely the images under this quotient map. Okay, x1 bar power I1, xn bar power In in K. Again, this is countable. But the point is, what we have told is C of XR, the function field, is lying inside, sitting inside K. But function field, already by a lemma, we proved this function field has uncountably many linearly independent elements. Okay, so uncountably many linearly independent elements this C of XR has. Okay, so this is sitting inside a field which has countable basis, which is a contradiction. Okay, this contradiction implies that this contradiction. Why? Because this C of XR already we have seen last class. Okay, I have this notes. I will show you once more. Okay, this is the last proposition. You see the function field in one variable, okay, has uncountable set of linearly independent linearly independent elements. That is look like 1 by x minus alpha, where alpha belongs to any complex number C. Okay, because of this, since this function field is sitting inside a field K, where the field K has countable basis. These two are contradictory. You cannot have uncountably many linearly independent set having countable base. Okay, so this contradiction really says that the kernel pi r is non-zero. Okay, since r is arbitrary, whenever we restrict to any subring of one variable C of x1 xi, then kernel of that restriction map is non-zero. Okay, okay, kernel of again you fix r, any r in between 1 to n, and we are trying to prove 2. What is 2? 2 is that the kernel of phi r is a maximal ideal. That's what we have to prove. It's an ideal, we know. We want to prove it's a maximal. Okay, you take any element inside f of xr in the kernel, be a non-zero element, because it is non-zero already. Therefore, there exists a non-zero element. You call it f of xr. Since K is a field and it is not a zero ring, therefore, this kernel phi r cannot be the whole ring. I mean, kernel phi r, if it is the whole ring, then what happens? Okay, so then what happens? The ring homomorphism phi r, its a restriction is the phi r is a ring homomorphism. 0 goes to 0, 1 goes to 1. If it is a zero ring, suppose K is since it is a field, it's not a zero ring. Therefore, this cannot be whole. Why? Because if it is whole, then this will be zero only. This I mean C of xr modulo the kernel is going to be just a zero element. Okay, zero element is isomorphic to okay. This is okay. Since K is a field, it is not a zero ring. Therefore, it is not. Why it is? If it is whole, what happens? If this is whole, okay, my logic somehow forgot. Because you see, we if we have to prove something, it is a maximal ideal, we need to prove this. Okay, this kernel, this ideal is cannot be unit ideal. Okay, so for that, whatever element I have taken, first of all, it is non-zero element, at that I know. K is a field and it is not a zero ring. Since it is not a zero ring, why this is not a unit ideal? Why this is not a unit ideal? If it is unit ideal, what happens? It is non-zero, but it's a unit ideal. Somehow I'm not getting. Okay. Okay. So suppose we assume and then proceed. Let me see whether I can come back to this point. If this is not a unit ideal, then we can choose one non-zero element which is not a constant. Of course, there is no element will be unit inside the kernel. Okay, so it means f of xr is not a constant polynomial. Okay, since f of xr is not a constant polynomial, this is over C. Therefore, f of xr is divisible by a linear polynomial xr minus ar. You call it for some ar in C. Okay, over C, this is divisible because it is one variable. Okay, so by fundamental theorem of algebra. So this means that f of xr equal to the linear polynomial times g of xr. When we apply pi r, okay, to this, then pi r of f of xr is same as pi r of the linear polynomial times pi r of the g of xr. Since f of xr is in the kernel pi r, then that is pi of f of pi r of f is 0. So this means what we have is 0 equal to the product of two elements inside the field K. Since K is a field, it is an integral domain. Therefore, one of them should be 0. Either pi r of xr minus ar or pi r of g of xr must be 0. Okay, so if pi r of g of xr is 0, then the degree of g is strictly less than degree of f. In fact, it is one less than. Then we can apply the same procedure to really get pi r of xr minus br equal to 0 for some linear polynomial we can able to get. That means, what does this mean? We are trying to get one linear polynomial inside the kernel pi r. Okay, so once a linear factor enters the kernel pi r, then that once some element is there, then okay, when we generate an ideal by this linear factor, that is contained in the kernel. pi r, which is again, I am assuming that is not a whole ring. So, but by the theorem, this is a maximal ideal generated by single linear factor is a maximal ideal. Okay, every maximal ideal in C of XR will look like this, and this is a maximal ideal. Since it is a maximal ideal, this has to be equal to kernel pi r. So the crucial fact is that kernel pi r should not be the unit ideal. Okay, so this, hence I have written, we have to think about it. Okay, so once we prove it is a kernel pi r is a maximal ideal by the same theorem, I mean, this already we are giving an explicit proof, which is equal to, it is generated by single linear factor. Okay, this is true for every r equal to 1, 2, 3 up to n, because r is any index, arbitrary index. So what we have proved, okay, so what we have proved is, so what we are trying to prove, first we start with the maximal ideal m. Okay, general maximal ideal m. We want to prove that this m is nothing but ma, where a is some point in Cn. Okay, that ma is nothing but the kernel of the substitution homomorphism. Okay, with respect to that point. Okay, this is what we want to prove. For that, what we are doing, we just look at the quotient ring modulo this maximal ideal. Therefore, we get the quotient ring is nothing but the field K, and we look at the canonical homomorphism or projection map pi from the polynomial ring to the field K. Now we are keep restricting this canonical map to the subrings C of x1, C of x2, etc., C of xr. Okay, so all subrings we restricted, and we looked at that the kernel of restricted homomorphism is not trivial, and also the kernel pi r is a maximal ideal generated by xr minus br. This is what we have proved. What we are going to do is this x1 minus b1, x2 minus b2, etc. These are all the elements of m. We are going to say that. Okay, that's why we are doing the restriction map. Okay, so how these are all going to belongs to? Okay, what we have shown that kernel pi equal to m, and the restriction map, of course, this is a canonical map, therefore kernel pi has to be m, and the restriction map to each subring, that kernel is generated by the linear factor xr minus br. Since pi r is a restriction map of pi under this subring, the kernel pi r is nothing but the restriction of kernel pi with the ring C of xr. Okay, kernel pi r is same as C of xr, the polynomial ring in one variable, intersection kernel of pi. Kernel of pi is m. Okay, kernel of pi is m. Therefore, kernel of pi r equal to C, the polynomial ring in one variable xr intersection m. Therefore, since the kernel pi r is generated by linear polynomial xr minus br, this linear factor is inside m also for all I equal to 1, 2, 3 up to n. Since then we generate this ideal generate the ideal generated by this all n factors, linear factors. That is nothing but mb, right? This looks like mb. Any mb will look like this one only, where b is nothing but b1, b2, bm. Okay, that point. Okay, so this is contained in m. Already we know mb and m are maximal ideals. Both are maximal ideals. Therefore, this has to be equality rather than subset. Okay. Here, main point is just a restriction map. Okay. So once you take a maximal ideal and look at the quotient ring, which is a field, and then canonical map you take from the ring to the quotient ring, which is a field K. Then you restrict to the n subrings. You look at the kernel. that kernel already, why we are looking at the subrings? Because already we have studied polynomial rings in one variable. What are the maximal ideal will look like? That is the reason we are looking at the kernel of pi is a maximal ideal there. Therefore, we can able to get one linear factor. It's generated by linear factor. That linear factor you lift it to that maximal ideal m. That does the job. Okay. So this Hilbert Nullstellar and Sartz, it says that every maximal ideal in the n variable polynomial ring over C is correspond to a point in Cn. Okay, that's what it says. Okay, so far what we have studied is we looked at polynomial rings. We studied polynomial ring, the quotient of quotient ring of polynomial rings. Through that, we could extend the ring notion to extension ring. Okay, and we studied one particular homomorphism called substitution homomorphism. Using that substitution homomorphism, we could clearly mention all the maximal ideals of that polynomial ring using this theorem. Okay. So far, this is what we have studied so far. So now we are getting into the 8th section of that book. Okay, this is called Introduction to Algebraic Geometry. Okay, some geometric object we are going to define. This is very naturally existing. You will see that after the definition. Okay, let V is a subset of the C power n. Okay, C is a complex numbers. V is a subset. V is said to be algebraic variety or variety if V is a solution set of finite number of polynomial equations in n variable. Okay, that means V consists of points a1, a2, an in Cn such that f1 of that point A is 0, f2 of that point A is 0, etc. fm of that point A is 0. Simultaneous solutions of this polynomial equations. Okay, you collect all the solutions. That set is called algebraic variety. It's a notion. Okay, or variety. V is a subset of the Euclidean, complex Euclidean space, n C power n. Okay, so okay, I have given some examples. Naturally, anybody can think of some example of this particular. Can you give example of a algebraic variety? One example.
A circle or a parabola.
Okay, circle. How?
It is the zero of the polynomial x square plus y square minus 1.
Okay, x square plus y square minus 1. In fact, any circle of any radius, its unit circle is not necessarily. You can take a complex number a and x square minus y square minus a equal to 0.
Any point a comma b in R square.
Okay, how?
X minus a into x minus b.
X minus a equal to 0, y minus b equal to 0. This is the two.
Equal to 0.
Okay, there are two equations. Okay, this is okay. Any complex line, any line. Okay, that is a variety because ax plus by equal to c. For some complex numbers, it is going to satisfy. Okay, it's a single equation. A point is a singleton point is going to be a variety. Why? Because x minus a, y minus b is 0. Okay, this SL2C, this is a variety. Can you see? Of course, you have to identify any matrix group. You can identify two. Here, I have taken the entries from complex numbers. Therefore, you 2 by 2 matrices. There are 4 entries are there. Therefore, each matrix I correspond to a point. Okay, each matrix I correspond to a point in C4. Okay. Once I have this, can we think of this SL2C is a algebraic variety?
1x3 minus x2 x4 minus 1
Okay, it's
equal
a
to 0.
single equation. So x1, x2, x3, x4. In 4 variables I am taking. The polynomial is x1, x4 minus x2, x3 equal to 0. Okay. The set of all, okay, set of all A, B, C, D in C4 such that AD minus BC minus 1 equal to 0. Okay, minus 1 I missed it. Okay, so this we can write it as a polynomial. This is the polynomial x1, x4 minus x2, x3 minus 1. So this is a algebraic variety. So many objects, naturally, it's a solution set. Okay. Okay, this Hilbert's Null sorts, what it provides a link between algebra and geometry. These are all geometric objects because it's a subset of C4. Maybe we can use topology, we can use geometry property, etc. Okay. So, but Hilbert Null sorts, it is just connecting these two objects. How? It says that the maximal ideals in the polynomial ring corresponds to points in C power n. Okay. So that's first of all, Hilbert Null sorts only says that much. Maximal ideal and points. We here varieties are points in Cn. Okay. So this correspondence can also be used to relate algebraic varieties to the quotient of quotient rings. Can you think of this? It is very natural from the Hilbert Null sorts and this variety. Variety means what? It's a solution set. Okay, defined by some polynomial equations. What we can do, the polynomial, all the F1, F2, F3, Fr is the R polynomial. This variety is defined. Okay, then we look at the ideal generated by these polynomials. We look at the quotient ring C modulo I. Okay, there we study the maximal ideals. Maybe this maximal ideal are going to correspond to the elements of the variety. Okay, that's the precise because you see here Hilbert Null sorts, it's just says set of all maximal, I mean whatever maximal ideals in the polynomial ring in n variable is corresponding to a point. Here if we take the variety, the points are very special. They're very special in the sense it satisfies some polynomial equations. Okay, it's a solution of polynomial equations. Therefore, that polynomials can be generated as an ideal. You quotient it. It means if we study the maximal ideal, this is the right. I mean, from Null sort, this is the way to look at variety. This is the theorem, in fact. Okay, let F1, F2, F3, Fr are polynomials, and let V be the variety defined by the system of equations Fi's. Okay, it means simultaneous solutions over C is all the points is nothing but V, the variety. Okay, let I be the ideal generated by F1, F2, F3, Fr in the polynomial ring C of x1, x2, xn. Then the maximal ideals of the quotient ring are in bijective correspondence with points of V. This is very natural. And the proof is also just straightforward. Since ideals in R corresponds to the ideals in R, R means here it's a quotient ring I'm looking at. Okay, R is nothing but C of x1, x2, xn modulo I, ideal I. Okay, so any ideal in that quotient ring corresponds to ideal in the polynomial ring which contains the ideal I. Okay, that's the correspondence theorem we have seen. So now you can prove that it's a kind of little exercise for you. You can prove that the maximal ideals in the quotient ring corresponds to maximal ideals in the polynomial rings that contains I. Okay, same ideals in the quotient ring corresponds to ideals in the polynomial ring that contains I. Okay, same way you replace ideal by maximal ideal. That is also true. Okay, in fact, in order to prove, it is enough to prove that if F is a ring homomorphism from R to R prime, the quotient ring, okay, quotient ring R modulo J is the ring homomorphism, then I is a maximal ideal in R prime, the quotient ring, then F inverse of I is a maximal ideal in R. F inverse of I contains J, then only then we can, otherwise no. Okay. So this is just, you have to check the maximal property. This is true as an ideal wise. Just you assume that I is maximal in the quotient, and therefore F prime of I is also maximal there in the polynomial ring. Only maximality you have to prove. Okay, so any maximal ideal in the polynomial ring that contains I, if and only if I is generated by what? F1 F2 Fr. Therefore, that maximal ideal also should contain this elements F1 F2 F3 Fr. On the other hand, any maximal ideal in the ring, polynomial ring by Hilbert's null and sorts is of the form MA for some point A in Cn. Okay, which is MA is the nothing but the kernel of the substitution homomorphism from f of x going to f of x1 x2 xn going to f of a1 a2 an. Okay, hence, so once, okay, the maximal ideal contains I means maximal ideal contains f1 f2 f3 fr, but the maximal ideal is looking like m of a for some point a, okay, in Cn. So since f1 f2 f3 fr are inside m of a, that is if and only if this fi of a1 a2 3 ar an is 0, because it is nothing but the kernel of the substitution homomorphism. Okay, so that means whatever maximal ideal you take, it corresponds to one point through MA. Okay, since maximal ideal contains I, it means all the generators F1 F2 F3 Fr inside the maximal ideal MA. Okay, since MA is nothing but the kernel, that the substitute, when you substitute that the value A at each FIs, you get 0. That means simultaneous solution, this point A is a simultaneous solution for F1 F2 F3 Fr. That means the point A is inside V. These are all if and only if. Okay, so this is very natural. So therefore one can study variety through the quotient ring also, or some other in geometric methods also. Both ways one can study. This is the kind of connecting theorem. Okay, first one natural question: algebraic variety V can be empty or non-empty. Okay, we have defined only algebraic variety over C. Okay, when you change the field, etc., this question can change. The nature of the answer can change. Okay, here over C we are talking about. So whether algebraic variety will be empty or not, always. Okay, because of this previous theorem, it is equivalent to ask whether it is possible for a ring to have no maximal ideal at all or not. Okay, because of the previous correspondence, algebraic variety, every point corresponds to a maximal ideal. If V is empty, V is non-empty means there exists one point. One point corresponds to one maximal ideal in the quotient ring. Okay, C of in the quotient ring. So the question is whether given ring R has a maximal ideal at all or not. For which ring maximal ideal doesn't exist. These questions are equivalent right now. Okay. Okay, do you know this answer? Oh, already I have written, unfortunately, here. It turns out that this happens only for the 0 ring. Okay, the theorem says we are not going to prove this. Let R be a ring. Every ideal I of R which is not a unit ideal. Okay, I is not a unit ideal means I not equal to R is contained in a maximal ideal. Okay. So if give R is a ring, every ideal I not equal to R always contained in a maximal ideal. This is proof is using Zone's lemma. So we skip the proof. We are not proving. Okay, the only ring R having no maximal ideal is the zero ring. Why it is corollary to this theorem? Because only one element exists. Okay, that is nothing but zero ideal. Zero ideal is same as unit ideal because 0 equal to 1. Okay, in this 0 equal to 1 means it is a unit ideal also. Therefore, we cannot apply the previous theorem. I mean, the previous theorem is applied only when it is anyway. So, therefore, using this, we say that it doesn't have a anyway. It has got only one ideal also, which is nothing but the unit ideal. Okay, zero ideal or unit ideal. Okay, so not always this. I mean, if R is ring, then one has to use. I mean, existence of maximal ideal. One has to use Zone's lemma. But the point is, for when R is a quotient ring of a polynomial rings, okay, then Hilbert basis theorem can prove the existence of maximal ideal in R. Okay, if R is nothing but the quotient ring of a polynomial ring, not always one needs to go to John's lemma. Okay, this is just from the algebra itself one can able to prove. Okay, so the next comes. So the okay, so we are kind of asking for, we just randomly pick up some 4 or 5 polynomial in n variable, and we are checking whether, okay, by the previous theorem, of course, there exists. No, what we are asking is whether it has a common solution or not. Okay. Okay. Suppose if it doesn't have a common solution, what happens? Because all polynomials, suppose random polynomials, if you choose 2 polynomials, it may not have a common solutions. Okay, in even C. Okay. So what the previous theorem says is that, you see, if there is a common solution, then okay, I don't know what. Okay, the previous theorem, what it says, if V is a variety, it means if there is a common solution, then we can able to connect. This theorem says we can able to connect to the maximal ideal. Okay, or any ring R will have a maximal ideal, but it R will have a maximal ideal. But the point is, this I is not given to us. Okay, is this, you see, if F1 F2 is not having common solution, then this I will be like a whole ring R. This R will become, this quotient ring will become 0 ring. That's what we have to check whether it is, if there is no common solution, whether this is going to happen or not. Means, okay, so this is the thing. F1, F2, F3, Fr be the given polynomials. If the system of equations has no solution in common, okay, then one is the linear combination of this Fi's. It means the ideal generated by F1, F2, F3, Fr is the whole ring. Okay, then of course the quotient ring is becoming a 0 ring. The 0 ring doesn't have a maximal ideal. Okay, therefore the corresponding V will be empty. Algebraic variety will be empty. Is it clear what I'm saying? So here first we assumed in this theorem. Okay, so I will recall once more. In this theorem, we are kind of assuming that V is a variety defined by the linear system of equation. Okay, so this variety is empty or non-empty depending on this I is a, this R is a 0 ring or not. If R is 0 means I is the whole ring, the unit ring, unit ideal. Okay, I is a unit ideal. The R is a 0 means if R is the 0 ring, then there is no maximal ideal, therefore there is no corresponding point here. Okay, so that is the reason first we have to really check that if there is no common solution, then the ideal generated by the F1, F2, Fr is indeed the unit ideal. Okay, so why it is? Assume that the system has no solution. The system has no solution means this implies there is no maximal ideal containing. Okay, there is no maximal ideal containing the ideal F1, F2, F3, Fr. Why it is? Because if there is no common solution, the first theorem, the previous theorem says, if I go modulo this, there is no maximal ideal. Then by the second theorem is nothing but this existence of maximal ideal. Okay, by the second theorem, by the second theorem, the ideal containing, by the second theorem, I must have unit ideal. Unit ideal means it is whole ring. Okay, so therefore you can write one as in the linear combination of FIs. So if you randomly you choose one polynomial in one variable. Okay, randomly if you choose one polynomial means what? You are arbitrarily putting coefficient and some arbitrary degree you are making. Okay, so the thing is that is always going to be irreducible. The probability is almost one. Probability is one for which this is going to be irreducible over whatever field you consider. Okay, over Q if you assume. Okay, so likewise, if you take two different polynomials randomly, if you choose in n variable, it's not needed that this will have a common solutions. Okay, we will see in only case n equal to 2 case in some sense little more detail next lecture why this is true. Okay, in general you cannot expect common solutions always. Even in linear equation, if you take, you see it is not necessary that it should have, but of course we know how to solve the linear equations very well. Okay, so the Null sorts, what it said, it is studying the maximal ideal in the polynomial ring in n variable, how it will look like. Any maximal ideal will look like it's generated by linear factors. That's what the Null sorts what we have seen. The original form is something different. Okay, what it says, it is in terms of variety. So let F1, F2, F3, Fr are given polynomial ring, given polynomial in the polynomial ring, and I is the ideal generated by this FIs. Okay, then let V be the ideal, V be the algebraic variety defined by F1, F2, Fr. It means it's a simultaneous solution for these FIs V. Suppose there is some other polynomial. Okay, G is another polynomial which vanishes on all points of V. Suppose that means G is a given polynomial such that G of A1A to AN is 0 for every A1A to AN. The tuple belongs to V. Then the power of some positive power of or non-negative power of G should be inside the ideal. The ideal captures G power N. Okay, the given polynomial will be inside the ideal, the power. Okay, for some power, we don't know what is N is. N can be 1 also, N can be something more also. Okay, this is what the classical form of null sorts. Okay, so in order to prove, it's going to be a trick. Okay, So while dealing with extension ring, what we did, suppose we want to attach the inverse element to the ring. Suppose some ring R did not some element alpha inside R which doesn't have the multiplicative inverse. I want to push it inside. I want to get an extension ring R prime such that R prime contains this inverse of this alpha. Suppose, then how we did this? We looked at the polynomial ring Rx and we went modulo ideal I generated by what? Alpha x minus 1. Okay. So we want to push that inverse element. We want to adjoin the inverse element to the given ring R. So what we looked at the polynomial alpha x minus 1. Okay, so if there exists some x solution to this, it means I will get the inverse of alpha. Okay, so likewise we are going to do here. G is an element given in this ring. Okay, what we are going to do, we are going to kind of insert the inverse of this element. It means we are going to look at this polynomial g of x1 x2 xn times y equal to 0. Y is a new variable. Okay, so that means we have to go modulo something. Okay, already there is an ideal I is given to you which is in n variable f1 f2 f3. It's generated by f1 f2 f3 fr. What we are going to do, we are going to look at r plus 1 polynomial including this polynomial, but in n plus 1 variable, because n variable polynomial is also inside n plus 1 variable polynomial by treating xn plus 1, that is nothing but y, as if it is y is existing in this given the fi is also. Okay, we are going to look at r plus 1 polynomials in n plus 1 variable, where variables are x1 x2 xn and y. Okay, here there is a typo, 0 I should not write. I just put y only, 0. Instead of 0, I put y here, and h prime, I put x1, x2, xn. That is just I didn't kind of y variable y only comes, rest all x's doesn't come. Okay, so we are looking at n plus 1 variable polynomials, r plus 1 polynomials. That is f1, f2, fr is given. And one more polynomial we are looking at, that is g of x1, x2, xn times y minus 1. Okay. Okay. F1, you can call it just f1, f2, f3, fr. G, h minus 1. H is nothing but only one y variable is coming, the rest of the x's are not coming. Okay. So some r plus 1 set of polynomials we have in n plus 1 variable. We claim that, okay, these are all, these polynomials do not have common solution. I mean, simultaneous solution doesn't exist for this in c power n plus 1. Okay, is it clear to people why these polynomials don't share any common solution? Okay, just we take a point, okay, random point a1 a2 an comma b, where a1 a2 an is coming from the variety v. Okay, when we plug this point in fi's and the gh minus 1 also, what we get, you see, this is, since it is coming from variety v, fi's are going to be 0. The y variable is not there at all in this fi's, therefore whatever value b you put, it doesn't matter, it is going to be 0. Similarly for g also, y variable is missing here. Okay, but the point is, since g is also 0, you see g is also 0, then gh minus 1, that becomes at this point is minus 1. It is not becoming 0. Okay, whenever the first n coordinate coming from the variety v, b can be any random point, then these points never vanishes simultaneously. Okay, okay. So I take a point b1, b2, bn and b. which is for which that last polynomial is 0. First we have taken points so that the first r points are first r polynomials are becoming 0. Okay, here I am taking a point such that the last polynomial is becoming 0 when I plug x1 equal to b1, x2 equal to xn equal to bn, and y equal to b. That means g of b1, b2, bn times b equal to 1. Okay, here I can assume that b is non-zero. If b is 0, b is 0, then okay, b is 0 for these points. Okay, first I assume that b is non-zero. Okay, if b is non-zero and these 2 points are multiplication is equal to 1 in C. Okay, so this implies that this cannot be 0. Why? Because this b has inverse in C, and C is a field. Okay, therefore g of b1, b2, bn is non-zero. If g of b1, b2, bn is non-zero, means this point b1, b2, bn is not in the vector, I mean not in the variety V. Why? If it is in the variety V, then g will vanish. That's the assumption, hypothesis. So once b1, b2, bn is not in V, then fi's are not going to be 0. Okay, fi's are not going to be 0. That means with b is non-zero, no point is lying inside. No point is going to be no point of Cn plus 1 with b non-zero is going to be simultaneous solution for this polynomial. If b equal to 0, then b equal to 0 means anyway b equal to 0 means okay, what happens here? It is never going to be 0. G h minus 1. If b equal to 0, then b equal to 0 means this polynomial gives you minus 1 only. Therefore, that is also not going to be 0 of that. Okay, b equal to 0, and you take any point b1, b2, bn, that if you plug it, this is not going to be vanishing. Okay, so what we have seen, this f1, f2, f3, fr and g h minus 1 have no common zeros in Cn plus 1. Therefore, by the corollary means since it doesn't share any common zeros, it generates one equal. We can write 1 as the linear combination of this particular polynomials. Okay, in the n plus 1 variable polynomial ring, or it's a unit ideal. That's the reason. Okay, so this is the way we are writing 1 equal to some polynomial inside this ring Pi. Fi is the usual one, and Q is another polynomial in this n plus 1 variable, and G y minus 1. That is the last polynomial. Here y is a free variable. We can put anything. Okay, so we are putting y equal to the inverse. Okay, actually we are doing the same construction, but we are not writing in some sense. We are just writing a kind of trick. Okay, so we are really doing the same construction as the quotienting with the gx minus 1. No, g of g times h minus 1 only. Okay, we are putting y equal to the inverse. Once we put y equal to the inverse of g in this, rest all, you see, g doesn't have a y variable at all. So now every variable is this pa is a rational function, but a rational function, the denominator is only g. Okay, nothing else, some powers of g, because since we are putting below, while clearing the denominator, what we do, just we multiply by some maximum power of the denominator. When we multiply both sides, the maximum power of the denominator, what we get is okay, gn of x1, x2, xn equal to, after clearing the denominator, multiplying by some power of g, then this becomes just a polynomial, rational function. There is no rational function here because we cleared the denominator. Okay, in fi's anyway there was no g, so therefore what we could write is this power of g lies inside the ideal generated by F1, F2, F3, Fr. That's the null Stalin sorts. Okay. Okay. So we have defined something called a geometric object, which is called variety. That null Stalin sorts says that if given a variety, either you can study as a geometric object or you study the maximal ideals in the quotient ring, corresponding quotient ring. Okay, so that is the link between variety and the quotient ring. And this says that if any other polynomial is vanishing on the variety, then the power of that polynomial will lie inside the generating variety. Okay, generating the ideal. Okay. Okay, this is for today. So next lecture, what we are going to see is that, okay, in general, for any n, just viewing variety is maybe hard. For n equal to 2, we try to see what is clearly the variety, algebraic variety means. Okay, there is a description, very simple description is there. This null Stalin sorts in this form. Okay, I have a kind of remark. Okay, in this form, there is a recently in the sense of 1990. Okay, 1990, there is a combinatorial version of null Stalin sorts came. Okay, which was proved by Nagalan. Okay, which follows this kind of similar, but objects are going to be different. Okay, this is here over C, this is a polynomial ring, their objects are going to be different, but the same setup. Okay, so that is kind of very powerful tool to prove some combinatorial kind of results. Okay, that is called it is in the setup of polynomial methods. Okay, null Stalin sorts, combinatorial null Stalin sorts. Okay, with this I will end today.